Bogdan, who is a typical host of our R&D talks, but he took a few days off, so I'm replacing him. I'm also from R&D, so this still counts. Thank you for joining today's session, the first one in 2024. Thank you also for your continual interest in R&D talks, or probably if you're a new one for this to this session, thank you as well. And we promise to pay you back with interesting, exciting, deep tech topics that we discuss on this platform. And today is exactly such case. Iurii Kobein will be presenting today. Iurii will share his experience from more than 15 years of working with research and development projects. He has experience in CUDA, high performance computing, and parallel processing, and a lot more. Iurii has contributed to multiple initiatives within R&D team. This one includes very early beginning of the 3D scanner, such customer projects like Koyan, Shell that was just recently acquired in 2023. And Iurii will speak on the subject, is HPC optimization effective or efficient? And so without further ado, Iurii, please go ahead. The stage is yours. Iurii, we don't hear you. Please, probably it's muted.
Okay, thank you for the presentation. Actually, okay, we can start. Oh. So the topic is a little bit controversial. So what the problem we try to solve, that effectiveness or efficient, because working with high performance computing and optimization in general, faced with the problem that we not always do efficient, however rely on effectiveness to add some more compute capability to solve other problem with losing efficiency. And it means that actually we can do better, and I will describe why and why do we need actually do it better. Firstly, the agenda will so firstly we will briefly go through the HPC market and why do we need it actually, some basic architecture of HPC system, what basic components it is consists, and some optimization challenges and some techniques that we face on our daily basis when we're working with a client, and how we can actually achieve this efficiency, and some just thoughts about the future. And okay, so regarding firstly, I would like to go in reverse order. Why do we need it actually, this HPC from the market? The market demand it, and according to the forecast and some business analysis, the market grows and it grows constantly and requires expertise every year. So, and especially that our component based application, and this application, this component is required good expertise to actually address this business needs, as well as besides that, as service grows, the demand, the networking devices and everything need good expertise to bring our best to the business. So actually, and the main idea that as far as the demand, we need to dive deeper in it and to constantly grow. Also, what actual the application areas that is requires HPC is mostly is education and research. like discovering like life science, also government and defense. For example, it's very banking and financial services, insurance, that actual also rely a lot of HPC system, because even it's like it's very real time system that requires very efficient solution, because who first analyze and produce the forecast that win on the next day. Media and entertainment, healthcare, and energy utilities, game dev, and a lot of others applications. And that brings us to this topic that HPC is like the correct way to resolve this problem. And actually, HPC is a system of distributed computer resources to address this complex problem. And it composed of like some on high level for like nodes. It's computer cluster and high performance computer resources and components like interconnect those clusters between each other, and actual parallel computing node that performs some heavy and computation intensive work and intensive work. Here we like to give you a brief, not comprehensive, but brief idea of some node of HPC system and some key characteristics that should satisfy. And so first of all, it's like as I said, a distributed system, and the system should be scalable. It means that for the big enough problem size, we could able to add new computer node and be able to resolve the problem in some satisfied timeline. Also, in order to do it think efficiently in terms of latency and bandwidth, we need high-speed interconnects between those computational nodes, and like InfiniBand, remote DMA over the net, and some other protocols and hardware. Also, high bandwidth storage system is required to store the all necessary information with high computational power, like accelerator. It could be Intel, NVIDIA, AMD, etc. And of course, everything is governed by a scheduler and resource manager. So probably we have some user that just compose its HPC program, and via login head node distribute it evenly on each node and start computation. So as I said, the node, the cluster is composed by HPC node, and each HPC node could be is actually multi-core processor, and also could be host some additional accelerator like GPU or even FPGA, and to address those intensive computer like requirements. It could be like unified multi-core processor or mix of multi-core processor and GPU, known and heterogeneous computing. And most popular solution is Intel, AMD processor, NVIDIA, that actually addresses those problems. And all those nodes, as I said, connected into the cluster. However, in order to be able to do it with low latency and high bandwidth, we required some very good interconnection. And for this goal, we have different protocols like InfiniBand. It has very low latency and high bandwidth. Also, some canonical conventional Ethernet could be used. It's even sometimes more suitable due to high due to this protocol, and hardware is quite popular and available and not need any specific tuning. I mean, you need to tune, but it's like interchangeable. Also, for small clusters, we could use even PCI Express or another like vendor-specific technology like NVIDIA NVLink or some new Gen Z protocols. And on the picture, we see just the InfiniBand topology of HPC cluster, how complex it could be, and what actually the problem size that could be run on those clusters, and how it's like one of the flavor of the HPC system. Also, another important component is storage system. For it should be sufficiently satisfies the requirements for storing data. And here we can have like Lustre, IBM Spectrum, and different other file system that actually address especially HPC problems. So I want just to recap that actually like common HPC system is composed of 4 components: is interconnection, storage, servers, and software. And actually, as R&D, we mainly work with the software part, and especially implementation, like on application applied level implementation algorithm and optimizing them. Of course, software could contain some drivers, stuff, orchestration, scheduling. However, like our main focus is on optimization technique for algorithm itself. So with this general picture, I would like to give a very brief story how actually our daily basis in my team looks when we dealing with some HPC problems. And one story, for example, the client researchers designed and implement algorithm for simulate some physical systems. The algorithm is fully parallel. It means that actually we can scale very well according to Amdahl laws and Gustafsson laws. So it's Amdahl laws like address for strong scaling. Let's say that actually each computational problem could have a parallel path that is ideally could be distributed between processing unit and have serial paths that could not be parallelized, and all scaling like is governed actually by serial path. You could not on this on if you have even unlimited parallel resources, all your performance limit to the serial part. However, Gustafsson law a little bit different, because actually with Adam's laws it's aimed to the fixed problem size. We fix problem size and looking for best, like optimal computer power to resolve it. However, there is a little bit weaker law that actually constrains Gustafsson law that said that actually we do not fix the problem size, we normalize the execution time. However, the problem size could grow, and as far as the problem size is grows, we could continue scale, even the efficiency is lower, like utilization of resources could be lower. However, the execution time can scale linearly. So the client's researchers designed and implement algorithm, it scales, and the expectations it should run perfectly on HPC system with high percentage of efficiency, but anyway, it takes too much time, and efficiency is low. And however, due to say that it is perfectly parallelized, the client said, okay, we can even scale. Yes, we have lower efficiency, but we can add more computational power on bigger problem sizes and still receive some benefits from it. However, another problem, yes, our bill from cloud provider is quite high. But anyway, the new customers are coming, so we can scale any more to satisfy our business needs. But at some point, it figure out that, oops, it doesn't scale. And from this point, actually start other work. The client came with this problem to us, and actually said, okay, we need your help to optimize this algorithm. We have some physical simulation algorithm we use for this particular problem. CUDA programming model. We use some cluster based on NVIDIA V100 and Y100. Our communication is InfIBand over MPI. And we need this in n times faster, consume less memory, and we can a little bit sacrifice the accuracy precision in some project, but in general we need like it could be in some controllable ranges. And actually after that, what we perform. So firstly, is we get the basic domain knowledge. We cannot analyze the problem without knowing just analyzing pure code, without knowing the physical moments, the mathematical, how the problem is modeled mathematically, what is it like the stability of system in terms of numerical method, and etc. So we firstly dive deeper into the domain knowledge to understand the problem itself and how this problem is modeled into numerical method. Afterwards, we going from a top-down approach to profiling entire system to have general view. In such cases, the cluster is based on NVIDIA technology, so we're using NVIDIA system to have the general view of the system performance in terms of CPU, host memory, GPU memory, and MPI communication to figure out the bottleneck. Of course, the profiling should run on different input data multiple times because actually we're interested in distribution of the of our not errors, but a distribution of the performance because it's not like the constant time. One time it could be faster, slower, and it's our the modern operation system is quite complicated and some it's a little bit unpredictable. Yes, and in order to neglect this, we should run it in multiple runs to actually get the distribution and freeze the software stack, of course, because we should use the same compiler, MPI protocol, and setter library that will be used on the client side to guarantee actually that our optimization work will be applied to on the client side. So, and the first thing that actually we discovered in this problem is that communication between nodes is not efficient. It uses communication via host memory that actually perform copying of GPU memory into the system memory, then copying this data from the system memory via chipset or writing directly to the NIC network adapter directly. That is, as we see on the left side, is quite inefficient. We have to copying. This copying also it should be done asynchronously, but however, it's a lot of work, and actually the code that manage it is quite complex. What we can use some good technique like GPU Direct that actually can offload everything directly to the chipset and only do not involve CPU at all. It has like two flavors. It's GPU Direct. It's for the system that, for example, one node hosts a few GPUs, or it could be done via GPU Direct, RDMA, Remote Direct Memory Access, on the multi-host version that actually allows copying the memory into different GPUs via a network adapter directly. It also has a beautiful side effect in terms of code, because the code is much cleaner and maintainable, and it's more natural. It's like mimic unique address space between two GPUs. However, also this communication could be carefully also tested on different problem sizes and the different sizes of the cluster, because it's also important to use some binding to the for example, each CPU should bind into some specific core of CPU should be binding to specific node in order to avoid unnecessary context switching between cores that actually creates some latency and synchronization. Another modern technique, actually, in order to optimize communication, is based on open SHMEM standard specification, actually. And for example, NVIDIA implements it in terms of NVSHMEM communication library. And the idea is that communication between multiple GPUs or could be done internally inside the CUDA kernel. And for quite big cluster system, it leads to that. Actually, one benefit also is we can have only one of few CUDA kernels that are unified. We don't have those special cases. For example, when for the big problem, we should have like main kernel that performs the computation, and then we should have some additional kernels that performs computation on the boundary where the problem is divided on. And this creates additional complexity and additional synchronization points, and everything could be fused into the one kernel. And And for the quite big problem sizes, this solution scales very well and is much more like promising and better rather than GPU direct. Another technique that also is very beneficial for MPI, for HPC, is compression. As far as, for example, in this particular example, we have communication, like all gather communication pattern with the compression. And for the big data, this could be bottleneck because a lot of data should be copied between nodes, create additional latency, unnecessary latency that actually does not address the problem in first place. And for such, in order to reduce this pressure on the communication, we could use some type of compression. We can use some lossless compression, but actually we don't lose anything. We just compress the, for example, for if we exchange some image, we just use some compression algorithm. Then the compression, of course, it's the beneficial of using this could be tuned and tested because anyway, compression and decompression is additional work that should be done. However, for some for particular problems, it's beneficial, especially for images. Yes, we can compress something, send into the, another node and decompress. Another type of compression could be lossy compression. Actually, we lose something. However, it's more, it doesn't have this additional overhead. We just, for example, on the boundaries of the other node or the other problem, when we exchange the data, we compress data from floating point 64 to floating point 32. And we lost some precision. However, in total, we win, like if the data that is passed is quite big, we win a lot. And this could also dramatically increase efficiency of the entire system. After communication, the optimization of the communication, inter-node communication, we actually go one step deeper and focus on the some computation node. And for cases, for our particular cases, it's like the CUDA. We could have first after profiling, we could have 4 different cases that will actually describe our limitation of performance. So in general, there's like 2 categories. It could be computed bound or memory bound problems. And for computer bound problems, we actually like spend most time of calculating, not accessing the memory. Like there is some categories of HPC problems that actually are compute bound, but very often, and in our practices, like vast majority, it's memory bound problem. That actually kernels for these categories we have 2 types. We have bandwidth bound, the transfer between the device and global memory reach the limitation. So it's like for each read from the global memory, we don't have enough working like instruction for computation, but actually we bound only on the bandwidth of the memory. So we need to read more rather than calculate. and latency bound when actually fetching from the memory is a bottleneck. So ideally, our utilization of resources it applies in general to any heterogeneous system with a GPU is about like 70-75% that compute and memory utilization. It's not the direct metrics, of course, we could be, however, it's like one marker. For compute bound problem, yes, we have a lot of computation, and the memory is memory pattern, the access to the memory, the pattern access memory is quite good. However, on each memory read, we have a lot of computation that actually is more than our available computation unit. And this type of problem, like D, is the most widespread that we like. It's problem for neural network, any CNN that utilize GEM algorithm. It's this type of the problem. It's it's memory bound problem. Also, we can, to address this memory bound problem, actually, we should know our data layout and very good, and or try to transform our data layout to some GPU friendly, as I said, presentation. So in general, we have two types of data layout: is array of structure. But for example, we have this 4 lattice points with direction, and for each lattice we packed its quantity together for each lattice. It's like the called array of the structure. And another approach is the structure of array, when we pack it by, for example, direction. For like each lattice point, we choose one quantity. So in such case, we have, in order to achieve to get the element for one direction of lattice, yes, they all packed together. For CUDA and for some even CPU application, it's more preferable layout because it's more cache friendly, and for CUDA it's also not about only cache, but also about the architecture. Due to on the CUDA we have like a single instruction, multiple thread, and each thread is run on minimum quantity on one warp, that is 32 threads. In such layout, each thread will receive consequence data. So in general, we will have less transaction from global to cache in order to fetch all the data and feed it to the particular kernel. And also there is like configurable, it's called collective structure of array that packed it by some stride. It's like general case, and this collective structure of array depends on the stride size. Could be transformed into array of structure purely, or structure of array. For example, if the stride size is 1, it automatically become structure of array. So for our needs, we often try to implement this pattern and then test the performance and behavior of system using different strides to choose more like suitable for particular problem. Some advanced techniques to working with the memory and pattern and layout could be in place pattern scheme. For example, for some problem, we want to read the data and change it in place without introducing new buffers, additional memory, if we have some limitation it, or vice versa. For some problem, we would like.
Sorry,
Yes.
we lost the voice. We don't hear it. Or is it on me?
Okay. Do you hear me?
Yes.
Could we continue?
Yes, Iurii, we can hear you.
Oh, sorry, it was me. Sorry. Apologies for interruption.
Okay. So, some advanced techniques of double buffering that actually create two buffers, or even could be three buffers, and in order to, it also depends on the particular problem. However, in order to avoid in-place modification, because it could be quite complex or inefficient in terms of access to the to the memory, we can read from the one buffer and produce some computation and write to, output to another buffer. Also, asynchronous reading, writing from the host or device in order to fully utilize the GPU and do not have this it's very beneficial when we have some like pipelined stage pipeline computation, and even on the new NVIDIA starting from A100, its compute capability 8.0, the asynchronous read from device memory into the shared memory was introduced, that actually allowed to create the staged pipeline inside of the kernel. So we can fetch the memory from the global memory into the shared memory, avoiding cache and avoiding involving of register, and purely asynchronously. And this allows us to have some initial fetch stage, and afterwards we can concurrently fetch from the global memory another batch of data and actually start computing the previous fetch stage. It's quite efficient technique, and for example, it's for gem problem, it leads, it's quite simple in general in terms of implementation with some minor tuning, but it leads to automatically increasing of performance about 50-20%. So depending on the patch size, however, it's like more advanced technique. And the final is better GPU utilization. Of course, it's this particular, we're talking problem with CUDA. We're talking about CUDA. However, in general, it is also applied to another heterogeneous model like MROC and even Intel GPUs. So we can prop different split of like grid block configuration to choose the optimal one that actually utilize the hardware resources the best. And one also crucial moment regarding optimal resource usage is optimal register usage. Actually, register file is quite limited, and if, for example, for some reason a lot of register allocated per thread, it's avoid to schedule enough number of warp that leads to a low utilization of streaming multiprocessor, that leads to low utilization in an entire GPU in general. And for particular cases, what we have found that we have a redundant loop unrolling. Actually, loop unrolling create additional pressure on the register, actually, and also manual unrolled loop. For example, if you have some computation and we just unwrap it and without loop, we do it manually, and it's also allocates additional register and per thread, and also indirection access when we have some array of indexes that actually, so in order to access some indexes in global memory, we should read some intermediate array of indexes. And in order to optimize it, CUDA like cache this intermediate indices in registers, and we should take care of them. And for that reason, the allocation of register and how much it uses should be controlled very precisely. We, for example, could use manageable cache to save the register, and also take care about like manageable cache. It is the same as ACA shared memory, because it's also limited resources. For each SM, we have some very limited number of kilobytes of this short memory, and it should be very carefully used in order to not in order to like evenly spread it among all thread blocks. So as a rule of thumb for CUDA, 75% utilization is quite nice and could lead to good performance. So after applying all those optimization that I mentioned, the final we solve the scaling problem. Actually, this is like 22 numbers, even more, 24 numbers of A100 GPUs, and we have linear scaling. Like performance execution time, we have like more than 2 times improved execution time. And besides that, we also using smarter data layout and different approach for pattern scheme to represent the access to the data. We also able to, like in general, reduce the memory consumption in 2 times. That allows to, in general, execute like in 2 times more useful work for our client. So, and very interesting like observation, yes. In general, what I just mentioned, not in general, in this particular case, but in general, what all problems that we are working is less about computation, but more about efficiently moving data. Like there is a famous quote that actually HPC system transform computational problem to memory problem, and in general it's the case. We do not change in general in general we don't change the computational part, like mathematical part. We only working around the data to moving it smarter, faster, and to move less data. And what we just saw that it is like to reduce and moving and do smarter moving of data between nodes and storage from host to device and actually device to cache register, because computational is quite fast, yes, and it's very eager. However, our path from the memory to this computational unit is very slow. And in order to satisfy the appetite of the computational unit, we need to look for the shorter, best way to deliver this data to computational unit. And actually, it's like the most challenges. And right now, it's all innovation and researchers work regarding HPC are delivering this problem by data compression, like in runtime. Yes, for example, to automatically switch between double precision and single precision when it needed, and or analyzing the data in runtime and also to compress it. It's like a lot of research is around this area, and less regarding computational, because in general what we can do about computational, we can transform one computational heavy problem in similar or approximate another that requires less computer resources, but with cost of some precision. And also like some more, okay, it's like also the more general sum up that, yes, as I said, HPC problems is more about effective efficiency transfer of data, and in order to deliver the good performance in faster, we need better cooperation between researcher and engineer, because very often we have like two stages. Firstly, researchers introduce some algorithm with some basic implementation, and knowing without dive deeper into the hardware or even some another stuff that is important for optimization. And then it comes to software engineer that try to map this problem onto some actual hardware or working business solution. However, as far as some design decision about design was made wrongly in the first place, it requires a lot of re-implementation or additional work to deliver the optimal solution. And this cooperation in like the first place to think about the performance in advance could and will should actually speed up the process of implementation delivery is the better optimal solution. And another thing that actually I was focused, I made focus on CUDA. However, the market actually is changing, and more attention is now turned to the another accelerator, like AMD, even maybe some another vendor. So we also consider and using some abstraction framework that preserve good performance. However, satisfy portability problem that we don't want, actual client don't want to have a lot of CUDA kernels, for example, heap kernels for AMD, or some very specific OpenMP stuff for Intel or AMD CPU. It would like to have some unified language, but for example, it could be also it could be have different implementation, depends on actual accelerator, but the language is has a single language. And for this, for maintenance, portability, and like changing of the market, because for example, if something happened in a years and we will not have the NVIDIA, then it's we will have some AMD accelerator, or it will be AMD will propose some cheaper hardware. So for that reason, some framework for accelerator like OCCA, SQL, more or less OpenCL is very interesting, especially in for R&D, because they address this problem and deliver good enough performance, so it's satisfiable. But satisfiable, and we have like this portable and more maintainable code. And like takeaway is also the profile. We should firstly profile, and get the domain knowledge before any optimization. As I said, for example, sometimes someone took the tasks to optimize and firstly look at the mathematic model or mathematical part. However, as said, very often it's not the case. Very often the case is to optimize data path, how the data is transferred between the node or to actual computer unit. So the profiler should profile and understand what the profiler says for you. And only after that apply some optimization technique. And some meta thoughts, so in general, Moore law is dying. Actually, someone even said that it's dead already, and the cost of efficiency will grow. So we could not rely on the faster hardware. Even faster hardware, it means it's very energy eager, and the efficiency of it will also matter. Because at this moment we even have some additional metrics of efficiency, like energy efficiency. We could perform the same work, for example, with little bit lower frequency of CPU, of GPU, and consume less power and be more energy efficiency. And some rise for faster development of PC algorithm, like we need a synergy of researchers, software and hardware in one place, because the demand on market grows, and who first delivers the better solution, that company could win some part of the market. And do it in one place, so this energy is required together. So researchers should understand this. Software engineers should understand hardware, and research engineer, and etc. And some thoughts about innovation approach. It's like analog accelerators, because they, for example, for large language models problems, analog accelerator could be quite enough due to it satisfied the precision, and is in power, in terms of power, is in magnitude efficient. And also the tool for software writing could be and should be better. For example, there already some initiative for functional programming that actually has in concept itself robustness and very cool like principles built into the language itself, to combined with raw power of parallel computing. Right now, there's like bridge into like middleware is quite poor, as for me. So it's we need some innovation in this area. Actually, that's it from my side. If you have any problem or any question or comments, I would like to answer.
Thank you, Iurii. Thank you for sharing your very deep, but at the same time, practical, hands-on insights from previous experience, expertise, right? We are still like collecting the questions in case there are any. I had one myself. You shared the graphs by the end of your talk, and there were a couple. One highlighting the scaling of computations, and the second one was about accelerating of the time. So I just wondered what was on the y-axis of the acceleration of computations, and why the first one was linear while the time was not linear, right? Like on this one, yeah, what is speed up? Here, speed up times, and on the second one, we also have speed up time. So why are they connected? And if yes, why linear the other is not?
It's scaling. It's actually,
Mhm.
for example, if we are adding new computational units like GPU,
Okay.
we have some linear scale of performance, of speed up. It's not like one-to-one. Yes, it has some slope. But this graph is address the scaling problem, that actually if you have quite big problem size, we can scale linearly.
Just by adding GPUs, we
We add GPUs.
the right time. Okay.
This one is just address the it's number with like, for example, it's address the legacy part. For we had for example, on legacy 2 GPUs and compare with the like optimized code, we had about between 2.2 and 2.4 better speed up.
Speed up times. Okay, so do I understand correctly that the plot from 2 to 12 GPUs, each next GPU increases twice, or how can you?
I mean that
Yeah.
it means that on the legacy you have like one it was one. When you run this problem on the optimized software, you will have it in 2 times faster.
Okay.
I mean, it's like it's a comparison between like not optimized non-optimized code with the optimized code.
Okay. And then just when we have more than 12 GPUs, it accelerates even faster, right?
It's actually addresses problem that I shared before, that the legacy algorithm does not scale.
Okay. Now it's clear.
It does not scale, and for that reason, like, we continue to scale like linearly into, if however the legacy does not scale, it's
Okay.
has some communication issue with communication between nodes that is fixed in optimized version.
It's clear. And so this 2 times acceleration was for the old code. Even during its scaling interval, we still have twice faster code, right? After our optimizations.
Yes. Yeah.
Makes lots of sense. Thanks a lot. Okay, I think I have got confirmations that there were no more questions. I think anyway, like Iurii is our R&D cluster lead. Feel free to reach him out in Teams, email, right? If you have any messages of preference. Also, thanks a lot for attending this talk, Iurii. Thanks for sharing. Yeah, looking forward for many more exciting projects like the one we just discussed.
Thank you.
Thank you.
Have a nice day. Bye, everyone.
Bye-bye.